right, so we're in section 3.6 in our book. And we're going to talk about curve sketching. So we're thinking that we have to sketch a curve. We have some kind of function. We have a description of it, and we want to figure out what the graph of that function is going to look like. We have a lot of tools that we can work with. So what kinds of things? Let's throw out some ideas. What kinds of things would help us sketch a curve? What could we figure out? We have a function written down. What could we figure out that would help us sketch a curve?
Intercepts.
Intercepts. Sounds good. We can figure out where it crosses the x and the y axis. That'll help us get an idea of the shape. What's something else? Asymptotes. Nice. And what is something, when we're thinking of asymptotes, what's kind of related to asymptotes? So we have vertical asymptotes, right? That tells us where the function is undefined. What do the horizontal asymptotes tell us? Yeah. Approaches as x approaches infinity. There we go. So the horizontal asymptotes tell us end behavior, right? So end behavior is another, asymptotes are kind of related to end behavior. So I kind of put those two together. We can look at the asymptotes. We can think about the end behavior. What else? Relative mins and maxes. Okay. So this, we're kind of in the algebra area here. Relative min max. We're going into calculus a little bit. What else? Think easy stuff first. What's that? So we could go just kind of the plug and chug method. We could plot some points. So a table of values even. So if you're really confused, make a table, plug in some points. And if you wanted to do work hard enough, you could make a really large table and sketch your entire curve. So let's see, what else? Concavity. So kind of related to the relative min and max, so concavity. And related to concavity, inflection points. Oops. Out of practice. Anything else anybody can think of? How about if we go even further back, intercepts, how about just domain and range? There's some kind of limitation in the domain, limitation in the range. So that's another one I can think of. Anyone else have any other ideas? Let's think kind of more related to calculus, what we've talked about in calculus. So we have relative min and max, concavity, inflection points. What else? What other ideas about curves do we look at in Calc 1? Holes? Or, okay. And holes, when we when we have a hole in a graph or some other kind of strange thing like that happening, what are we talking about? What kind of calculus idea are we talking about? Continuity, right. So we can look at the continuity and discontinuity, holes, so those ideas are all kind of related. So if we know that there's some kind of discontinuity, depending on the function, there might be a step, there might be some other kind of something happening with the continuity. What's another idea that's, I kind of think of them kind of in the same kind of big picture with continuity? What happens with something like an absolute value function? What happens here at the... What's that?
Cusp.
One more time?
Cusp.
Cusp. So we're talking about what happens at a cusp? What can't we do at a cusp? Differentiate. So the differentiability. We might look at the differentiability of a function. That might help us analyze the function. Figure out what's going on. Did I spell that right? Differentiability. Yes. Okay. So it looks like we've got everything on my list except one thing. So we're thinking of, so far it seems to me that we're thinking of functions that look like this, like this. What other kind of functions have we looked at that give us some important information? Did you have an idea? No? How about trig functions? What other piece of information can we get from some kind of function like a sine curve or a cosine curve? Period. So periodicity, does it repeat? So is it periodic? So that gives us some information about a graph. So these are some of the tools that we can use to analyze and figure out what the shape of a curve is. Now there's one piece we're thinking of kind of analytical tools. What do most of us have that's extremely helpful? Calculator. Now the problems that we'll do, this would be when we're using these kinds of ideas. This is going to be like it would be a no calculator type problem. But some of the problems in the homework, they say examine the graph using the graph of the function using a graphing utility. So they're asking you to graph it in your calculator, find the intercepts, find the mins and maxes. So your calculator is definitely a tool that can be helpful. And especially when we start getting into polar coordinates and things like that, it can be really hard to graph those functions in polar coordinates by hand. So your calculator is really going to be a useful tool. So these are all the tools that we have available. We're not going to necessarily use each of these every time we analyze the graph of a function. These are just ones that are available to us if we have some kind of complicated function that we're trying to figure out. Any questions? Any other observations that we have on curve sketching? And again, we're kind of trying to ease back into doing some math and thinking in terms of calculus. So just kind of some general guidelines to sketch a curve. What I usually look at is domain and range. And that's usually not difficult to figure out just by looking at the graph. And we left one thing off here that that I had written down, and it's related to if the function is periodic. Does it have any kind of symmetry? Is it even? Is it odd? Does it have x-axis symmetry, y-axis symmetry? What kind of symmetry does it have? So that's another tool. I look at we want to find the intercepts asymptotes and look at the symmetry, if it has any. And then we're moving into calculus. We want to find the critical points. And from these critical points, we want to find our relative min, max, and inflection. So when we're doing these critical points, is there? I think Ms. Hine had a particular way, or you guys do you guys have a favorite way of dealing with the critical points? Do you make like a sign chart or something? I find sign charts pretty helpful. So you find your relative max and min, find the slope on either side of the sign charts. That'll help you find what your second derivative is in those particular intervals, to see if you're concave up, concave down, how things are changing. So a sign chart is helpful once you find your critical points. All right, so what I want to do is, one, I want to look at a couple of problems, just kind of talk about them from, these come out of the homework, but I want to talk about them as a class, and then we will go over, there's one example that I want to go over to make sure that there's one little tricky thing that we might need to think about when we're doing this. So let me grab these examples. They are here. All right, so here's the problem that we're looking at. So we have this function. We don't know exactly what it is, but f of 0 equals 3, and f prime is between 2 and 4 on the interval from -5 to 5. And the problem is asking us to find the greatest and least possible values of f of 2. How would we go about doing this? So we don't know what this function is. We know that at 0, the function evaluates to 3. And between x equals -5 and 5, the derivative is between 2 and 4. And we want to find the greatest and least possible values of f of 2. So let me do this. I'm going to pause this. So, who has an idea what we could do? What do you think, Josh?
Wrap it.
So you made a x and a y like so, and here f of 0 you put it like that. Okay.
And then I kind of figured that the f prime graph is the slope.
Okay.
And so it's either between 2 or 4. 2 is the least, 4 is the greatest. So if you do a slope of 2 between 0 and 2, that would be the least amount of the cube. And then if you use 4, that's going to be the greatest.
So you said that doesn't really matter what's happening in between here. We go in a straight line from point to point. We're going to, at the smallest slope, we're going to have the least value, and at the largest slope, we'd have the largest value. Sounds good to me. Everybody agree? Anybody else come up with a different idea? Anybody, did most of us see this idea of the slope and the straight line? Yeah. So part of what we're doing with curve sketching is, and with all of these ideas in general, is just getting to a point where we're kind of picking out information about our function. What does this tell us about the function? What information can we gather from the information we have? So that's what this problem is kind of about. We know something about the slope, and we know one of the values, so we can find this maximum minimum value. But this function could do a lot of things between here. It could do all kinds of weird things. But the smallest it could be is here, and the largest it could be is here. All right, let me grab another one, and this is my least favorite kind of problem. So here's our graph. And what we have here is a graph of f prime. And using this graph, we want to come up with a graph for f and for f double prime. So we want to graph f, and we want to graph f double prime. So let's work on that for a minute, and then we will talk about that one. So the secret to using this, you have to look at the screen when you write. It looks just like mine. It looks fine. It's about how I draw lines up there. So what are we looking at here? F or F double prime? F double prime. Okay. The easy one first. Okay. You can change the color if you want, just by flipping these little squares. That works. And you can undo here. But I think we get the point. We get the point. Okay. All right. Nice. Okay. Everybody agree here? Okay. Nice. Is that your first time ever using the one? Not bad. Not bad. All right. Does everyone agree with these graphs? The only thing that I did different on f double prime is I had an open dot here because we have open dots here and here. So that was the only thing different. And then I guess it's a little ambiguous here which one is open and which is closed. And then, so in between -1 and 1, we have a constant slope, so that means f is a parabola. If we found the slope, this would be f prime is 5x, so f would be 5x squared over 2 plus some constant. So we have this parabola. I only have one thing different here, is I had this line, so mine, what I did was I had my parabola here, like so, this line coming off, like so, and I had mine looked like this. So they didn't connect here. They can connect. Okay. Okay. So let's see. I said here the graph, the slope is the slope is 2. So this is so I said f of x is 2x. I guess we could have a constant in there, couldn't we? Okay. So I can buy that. All right. I'm good with the graph. So I take this back. All right. Questions on that one? Okay, nice work. Now let's go through quickly. I have an example of one where we have to be a little bit careful. And then we'll stop. So we want to analyze we're not going to go all the way through this. There's just one thing that I want to look at this having to do with this function. So we want to analyze and sketch this function. So we have this rational function. We can go through, we can find the minimum, maximum, we can find inflection points, that kind of thing. But there's one special thing that happens with this function. Anybody see what it is? There is a slant asymptote. Very nice. And why is that? The power in the numerator, the highest power in the numerator is 1 greater than the highest power in the denominator. So we have a slant asymptote. So our end behavior, we know that the limit as x approaches infinity, we can find the limit here. We could use L'Hopital's rule, whatever, however we want to do that. We know the limit is infinity, but the slant asymptote tells us how it goes to infinity. So how do we find, if we have a function like this, how do we find the equation of the slant asymptote? Remember? What'd you say? You divide. So to find our slant asymptote, we're going to do long division. Or I guess you could do, well, we can't. Yeah. Remember, synthetic division is you can only divide by things in the form of x plus c or x minus c. So since we have this x squared and an x cubed, we can't use synthetic division. So we have to use long division to find our slant asymptote. So do we remember how to do long division? I'm going to do x squared plus 1 out here and x cubed in here and put my division sign here. Made that a little high. And it's just like dividing long division of numbers. Do you remember how to do that? Most of my pre-calc students have a hard time remembering that one. And then we say, how many times does x go into x cubed? X, and then we multiply, so I get x cubed plus x, and then I subtract, and I always have to do this when I subtract so I get my signs right. So I get 0 here and a minus x. So when I do long division, so this is my remainder. So f of x, after I do my long division, another way I could write this is x minus x over the remainder over the divisor. So as x approaches infinity, this quantity is going to go to 0, and my asymptote is f of x equals x. So the slant asymptote is f of x equals x. And then that we can do the rest of the analysis based on the other tools that we already have. We can use find the relative minimum maximum, find the inflection points, find where the concavity changes, all that kind of thing. But when our power in our numerator, and there's 1 or 2 of these in your homework, when the power in the numerator is 1 greater than the power in the denominator, then you have a slant asymptote. You can have other shaped asymptotes. If this power in the numerator is too higher, then your asymptote is going to be a parabolic shape, and it just depends on how the function eventually gets towards that. But all we're going to look at is slant asymptotes. But there are other shaped asymptotes as well. So the homework tonight, there's some curve sketching, there's some problems like we did together as a class, just thinking about what the information is telling us. And I think it looks like a lot, but there are some that are like the ones that we did on the board, where they're not all sketching graphs. Okay. So here is the homework. We're on page 212. Number 31 is a trig function. And in your book, example 6 talks about trig functions. We didn't really talk about periodic functions, but you could look at example 6 in your book to get an idea of that.